Hi everyone, I'm Kurniawan. Today I'll be presenting our research paper titled Virtual Knowledge Graph for Federated Log Analysis. Log data analysis is a crucial task in cybersecurity information when monitoring and auditing systems, collecting threat intelligence, conducting forensic investigation of incidents, and etc. Current log analysis solutions such as SIEM systems store and index log message in a centralized relational database. However, this has limitations with respect to the ability to express a relation between entities. As we can see in the log, there are multiple usernames. However, we don't know what natural persons own those usernames if they are connected. An administrator would have to check this information, which is stored somewhere else. Another example is knowing what service typically run or should run on a certain port. Again, this information is usually documented somewhere else, inside the company or online available for standard ports but not obvious by looking at the log file. This gets even more complicated considering there are multiple hosts and devices in the network. Each host produces multiple log files in often heterogeneous formats. In this context, the collection and integration of log data in heterogeneous formats and from dispersed sources such as hosts and devices is a key challenge. Let's have a look at the existing solution. So basically, on centralized log management, they typically ingest log source from multiple log producing endpoints, parse message as a plain text, and index them into a central database before analyzing log data. As a consequence, it requires considerable amounts of disk space to store the data, as well as computational power for log analysis, which limits scalability. By contrast, in a decentralized log analysis, they partly shift the computational workloads involved in log preprocessing and analysis to the log producing host. They primarily aim to provide correlation analytics rather than query dispersed log data in a decentralized manner. As they continuously ingest all log data, they may consume a lot of local points resources. Furthermore, existing solutions lack semantic relation between entities that make it difficult to integrate partial and isolated views on system states and also to contextualize links and query log data. Based on this challenge, we identify several requirements for security log integration and analysis. Requirement 1. Resource efficiency. The approach should avoid unnecessary log processing, acquisition, extraction, and parsing, and minimize resource requirement in terms of centralized storage space and network bandwidth. Requirement 2. Aggregation and integration over multiple endpoints. The new approach should have the ability to execute federated queries across multiple monitoring endpoints concurrently and deliver integrated results. Requirement 3. Integration and contextualization and background linking. The approach should have the ability to contextualize disparate log information, integrate it, and link it to internal background knowledge, for example, IT assets, vulnerability, and external one, such as attack pattern. Requirement 4. Standard-based query language. The approach should use an expressive, standard-based query language for log analysis. We propose an approach called Virtual Knowledge Graph for Federated Log Analysis, a method to execute federated graph pattern-based queries on dispersed heterogeneous raw log data by dynamically constructing a virtual knowledge graph. Specifically, we introduce a method that extracts only potential relevant log message only on demand, while leaving log files remain on the host. It also provides integration among dispersed log events into a common graph via semantic graph representation. It also facilitates graph pattern-based query federation across endpoints that helps avoiding standard text search and are more precise. It also enables semantic linking to a background knowledge by delivering context information directly with the query. So what a virtual knowledge graph is? A virtual knowledge graph is a method for data integration for multiple heterogeneous data, also called ontology-based data integration, that replace the rigid structure of tables with the flexibility of graphs that are kept virtual and embed background knowledge. As you can see in the figure, virtual knowledge graph avoids exposing the actual data to the end users, but possible to query the data via SparkL query without really materializing the integration view. The graphs are also enriched by domain knowledge that allows users, for example, to perform inference and derive new implicit knowledge over the existing knowledge graph. Now let's take a look at the architecture of virtual knowledge graph for federated log analysis. Generally, it comprises two main components. The first component is query processor, a component that provides an interface to formulate SPARQL query and distribute the query among individual endpoints. And the second is log parser on each host, which receive and translate queries, process log data, and send the result back to the query processor. Now let's take a look at the details of these components and how they actually work. SPARQL Query Editor. It allows users to formulate and execute SPARQL queries against hosts. It also provides an option to define target host, time interval analysis, and background knowledge. Second is query parsing. The subcomponent parses the raw SPARQL syntax into a structured format such as JSON prior transferring the query to the monitoring host. The third query is a query translation. The subcomponent decomposes the SPARQL query to identify relevant properties for log sources selection and log line matching. And it will go to log extraction that extract the selected raw log lines and split them into a key value pairs representation by using predefined regular expression patterns. And then it will go to RDF mapping, which is a subcomponent that maps and parses the extracted log data into RDF. And after the data has been generated into RDF, it will go into RDF compression, which is subcomponents to compress the resulting RDF data into a compact binary format. And then it will goes to the query execution, which is in the query processor that execute the given queries against the compressed RDF data. And then in the end, this component or visualization component will present the query result to the user. Here is an example of the query parsing process. The left side is a plain SPARQL query, and the right side is a structured SPARQL query in JSON format that makes it easy to access variables and properties inside the query. And let's take a look at the query translation mechanism. As mentioned earlier, in the query editor we have query option and SPARQL query. In the query option, we can choose the targeted host, set the targeted background knowledge, K for knowledge, and set the analysis time frame. The SPARQL query, some information will be identified such as the prefix or namespace or identification of a vocabulary or ontology such as the log sources. And then the triple patterns is a statement in SPARQL consisting of subject, predicate, and object. For example, to look for a specific field or property in log sources. And then the filters that restrict the solution, for example, filter specific value for IP address. The log will be parsed and queried based on these criteria. Let's take a look at the example. The host one in the query option corresponds to the host, and then the Apache prefix that corresponds to a vocabulary that describes knowledge about an Apache log sources. We see the time frame corresponds to a time frame of the Apache log sources, and then the triple patterns containing has client property correspond to the log field, namely client IP. And then the filters that define a specific IP address of the client IP. And now we have the selected log lines as a result of the query translation. The selected log line will be parsed into a structured format such as JSON based on the extraction pattern. And then the structured log data will then be mapped into RDF representation based on our log vocabulary that describe the schema, terms, and their connection of log sources. And then the generated RDF graph can be linked to a background knowledge that describes more information about the domain, for example, the IT assets. Let's put them together. By formulating SPARQL queries, analysts can retrieve and dynamically construct log graph from disparate and heterogeneous log sources from multiple hosts and also link them to internal and external background knowledge. The generated log graph from each host and graph from background knowledge are sent back to the analyst through query federation and will be presented in an integrated view. We implement our approach by integrating a number of vocabularies, knowledge graph resources, and prototype tools that can be accessed publicly and reused freely. During our implementation, we also reuse several existing state-of-the-art libraries, and this is our prototype user interface for query processor. Let's talk about one application scenario for our approach. Scenario 1. Intrusion detection and background linking. In the scenario, we assume that an analyst is interested in additional information about vulnerabilities and potential mitigation from the EDS node log. To this end, the analyst formulates SPARQL query by leveraging the link between the SID object from EDS node alerts with the property has CVE reference from the EDS node rules and the value of CVE from the background knowledge. The analyst can get explicit information about the connected CVEs. Furthermore, it is possible to integrate other information such as attack impact scores from CVSS and potential mitigation from CWE. The integrated query results in the table show the original node message, the included CVE number, impact scores, as well as potential mitigation from CWE, including their IDs and description. Furthermore, the graph visualization shows the terms and their connection. Scenario number 2, network monitoring. In this scenario, we simulated SSH login activities across different servers, such as database server, web server, and file server, and then queried the outlog files with our federated approach. Now, an analyst can formulate SPARQL query to extract successful login events from SSH connection across hosts. By leveraging the link of out has out events entity into part event with a login event, analysts can restrict event only for login event type that actually not represented in the original log sources or only in the background knowledge. The table shows successful login via SSH over multiple hosts in the specified time range. The host type and target IP address come from internal background knowledge as the host name is connected to a specific host type. We evaluate our approach in a virtual machine using the systematically generated AIT log dataset. We include audit log, aperture log, syslog, exec log, and outlog. We split large log file from the dataset into small files to reduce reading overhead and improve log processing performance. We report the average times over 5 runs. Let's have a look at the evaluation results for a single host. We inspect 3 evaluation metrics for single host, including average log graph generation, dynamic log graph generation, and graph compression. The average log graph generation, we found that the performance for log graph extraction differs across the log sources. The overall log processing time scales linearly with the number of extracted log lines. Typically, the log extraction phase accounts for the largest proportion, or more than 18% of the overall log processing time. For the dynamic log graph generation, it shows an evaluation of the log graph generation performance with respect to the complexity of the log sources. Overall, the log graph generation performance grows linearly with the number of extracted log properties. Hence, queries that involve smaller subsets of properties will typically also have smaller generation times. And for the graph compression, overall, the compressed version is typically less than half the size of the original raw log and 10 times smaller than the generated RDF graph. The resultant graph output would be even smaller for few extracted properties, that is minimizing resource requirements such as storage or disk space. How about evaluation on multi-host? We measure the log processing time for multiple hosts on the same network using 7 hosts, 4 Windows and 3 Linux, and Windows host for log analysis. And for the dataset, we use the same dataset from AIT, specifically aperture log dataset described in the table that summarize the evaluation setup that consists of 6 experiments ranging from 30 minutes up to 5 hours. Host 1 to host 4 store the data from the original 4 servers in the dataset. Similar to the single host evaluation, for each experiment we report the average time over 5 runs. Let's take a look at the result. The figure shows the average log processing times for each experiment. Based on the result, we conclude that the growth of the log processing time as a function of the number of hosts is moderate. Therefore, this approach scales well with the growing number of hosts to monitor as the log processing on each host is parallelized. Conclusion. We introduce a novel approach for federated log analysis based on virtual knowledge graph. We have published vocabulary of virtual knowledge graph for federated log analysis, developed prototype, and demonstrated them in security analytics. We evaluate our approach in both single and multi-host evaluation with the result the log processing time of our approach is primarily a function of the number of extracted relevant log lines and queried hosts. And for the limitation, the log files are parsed on demand and not indexed. Hence, query parameters should restrict the extracted log line to keep the processing time manageable. And our knowledge-based ad hoc analytic is intended to complement but doesn't replace traditional log processing technique such as SIM system. And for the future work, we plan to improve the query analysis, for example, to make the automatic host and background knowledge selection. And we also plan to extend the virtual knowledge graph approach for log monitoring purpose, such as processing and querying the log streams directly in memory. Thank you very much